look at a graph to analyze Le Chatelier's lab, it can be at first a little bit scary, but it actually, if you really get into it, it actually can be used as sort of a check for what we did yesterday. So when this graph has all kinds of things going on, you can have one stress, you can have, this one has 3 spots where a stress has happened to the system. It really doesn't matter. It doesn't have to be a certain number of stresses, okay? So because most graphs you can't, or most pieces of paper that you photocopy cannot be done in color, what they'll usually do is whatever substances, if there's more than one reactant or product, they'll make them the same type of line. So in this case, both CO and Cl2 are reactants, and they are represented using dotted lines, and the CoCl2 is represented using a solid line. So when you get into figuring out what's happening in terms of Le Chatelier's principle and stresses, then you might want to highlight the lines a different color so that they stand out. It's up to you. And clearly this graph has not very good grid lines, so we are just estimating. We're still qualitatively saying increase and decrease. We're not saying how much is it increasing, how much is it decreasing. That'll be when we do 7.5 and we have actual ice tables, okay? So until about 5 seconds is a normal reaction like you would have thought in grade 9, 10, and 11. You have a lot of reactants to start with, and they start to be consumed. The product starts at 0, and then once the reactants start reacting, then it starts to get used up, okay? So from 0 to 5 seconds-ish is the forward reaction. Reactants are making products. Okay, and then if this was a graph like we did in the last unit, then the reactant concentration would eventually be consumed or go to 0, and the products would increase and then level off a bit, but then the line would stop. But our lines are not stopping. So we have the initial conditions, the initial forward reaction, and then when you get to about 15 seconds, the lines start to plateau, or they become level or not changing, or the concentrations become constant. And so every time you have a plateau in the graph is going to be equilibrium reestablished. And that is the whole point of Le Chatelier's principle. So we have equilibrium here because the lines are level. And then even though there is obviously something happening at 20 seconds, we can see this spike here. Eventually things start to adjust, and then plateau occurs again. 35 seconds, the lines are changing, and then plateau again. And then if the graph could be further extended, you can see here that the lines are starting to plateau again. So every time an equilibrium system is stressed, it is going to minimize or offset that stress according to Le Chatelier's principle. So we're going to be able to see that using our graph today. So from the first time it establishes equilibrium is from about 15 seconds to just before 20. just like day one, we're going to go through concentration first as a stress because even in just words with no graph, it is the most direct increase you have to decrease. It's a directly opposite change. But also, when you have a concentration time graph, then since concentration is directly being measured on your graph, it's also the easiest to see, okay, or visualize. So now, if you prefer colorful notes, then even with a highlighter, you can make the lines more colorful, okay? But you don't have to if the dotted line is enough for you. So on this slide, under the concentration heading, we have included 2 times. Time equals 20 seconds and time equals 45 seconds. And the reason that they are on the same slide is because visually they have the same change. So here's a spike and here's a spike. Okay, so you can say with certainty the stress or what has been disturbed is the concentration of CO at 20 seconds and the concentration of COCl2 at 45 seconds. So when you have a spike, whether these are both increasing spikes, you could decrease it as well, just like we talked about yesterday, then it's the reason you get a spike, unlike 32-ish, 35 seconds, where none of the lines are spiky, but they aren't level anymore. So the spikes correspond with the concentration. So because the y-axis is always going to be concentration, then the spike will always indicate a concentration stress. Okay? So in concentration on this slide, we're going to do the stress first and then look at how it's shifting. When we get to 35-ish seconds, then we're going to have to say how the lines are changing first and talk about the stresses last, okay? So there's 2 types of questions really here. So at 20 seconds, the concentration of carbon monoxide is increasing because that's where the spike is. That is the stress. So when you have a graph, it's unfortunate that 10 to 20 seconds here, the lines are kind of overlapping. When you make your own graph tomorrow for the lab, I encourage you to sort of spread everything out. These are just in general. Do you need to say what the increase is? No, you just have to say it is increasing. So the fact that the carbon monoxide stress at 20 seconds is a little spike, and at 45 seconds, the spike is much bigger. It's not really going to matter when we're just qualitatively saying increase. That means shifts this way. Eventually, if you were going to have to read the graph and do the math, first of all, you'd have to be given a better graph. Then you could actually say how much is it changing by. Okay, but for today, you can just say increase, decrease. You can say a small increase versus a 45, which is a big increase. It's up to you. So when you do a concentration stress, one of the strategies you can use is figure it out first and then use your graph as a check. Or if you're a visual kind of person and you would like to take a look at what's happening in the graph and then write your answer, it'll work either way. Okay? So when you have a stress and a response or result, then we still, yes, we have to follow Le Chatelier's principle, but we also have to follow the rules of chemistry. So if you have a concentration of one of the sides of the arrow increasing, whatever else is there is going to be increased or decreased as well. So if you notice the dotted lines and even initially, they're changing in the same way. Then at 20 seconds after the spike, changing in the same way. Both of them are gradually decreasing. At 32-ish, 35 seconds, both dotted lines are gradually decreasing. And then 45 seconds, they're both gradually increasing. So if the equilibrium is shifting towards the reactants, both reactants have to increase. If it was shifting away from it, both of them would have to decrease. So you have to still follow like the laws of a reaction, okay? So when we say, so if I wrote here, increase carbon monoxide, you could just say increase the reactants, increase in a reactant, and that'll work as well, okay? So if you preferred that if you were doing the homework yesterday, then it'll work here too, okay? So when you increase the concentration of something, then concentration is a direct offset. So if you increase the concentration of it, the system has to decrease it, okay? So yes, you could just say that, increase the concentration of carbon monoxide, then the result would have to be a decrease in the concentration. You could say the system has to shift to consume the added reactant. You could say the system has to shift away from the reactant. You could say, if you're a balanced person, you could say an increase in the reactant means the products have to increase to balance it out. All of those would be equal. So when you get a question like this, I'm going to write them all down. If it was like a test or whatever, you don't need to write them all down. So if one of them you really don't like and you don't want to put it in your note, you decide, okay? Okay, so all of those are the same thing. To consume the added reactant, away from the reactants, towards the products to balance the concentrations. Which would be a shift right or shift forward. And none of that we have to do using the graph. The only thing we needed here was to see the stress. So then you can check that if you've said, okay, if you increase the reactant, that means it needs to shift right or forward. So then what should we see in the lines on the graph?
I'm not sure I understand.
Okay, so if you have to consume the CO that has been added, that means that this increase should be followed by a decrease. So here it increases and then it decreases. Excellent. that we're on the right track. If you shift to the right or forward or shift towards the products, then if carbon monoxide, which is a reactant, is decreasing, if there is another reactant, it also should decrease. Does it decrease? Yes. If you shift towards the products, that means you're going to make more of them, and its line gradually increases. So we're right. You can write reactants gradually decrease, products gradually increase. That'll work as well. So when you have a graph, it's don't write this down, but every time, so tomorrow you're going to make your own graph. So when you have to decide, okay, it says gradually decrease, how much is gradual? Like I said, usually students don't like it when the lines cross. So if you gradually decrease it all the way across the other line, then that sort of gets ugly, okay? So this graph just has a little gradual decrease. We're not really stressed about how far it's going to decrease today, okay? So when you have to have a time, then you're going to check what's happening at that time. So at time 45, what is changing? We have this increase in COCl2, or you can say there's an increase in the product. Okay, so on the graph, the spike is easy to visualize. You could even put spike in the concentration if that makes more sense to you too, that's fine. Or product if you would rather. Okay, so the result is the same type of opposites change. So if you increase the product, then you have to decrease it, or you have to shift to consume the added product. You have to shift away from the product. You have to shift towards the reactants to balance out the concentrations. Any of those are the same thing. Okay, so if it's shifting towards the reactants, their line should increase, which they do gradually. If you're thinking of it like consuming the added COCl2, then that line should gradually decrease, which it does. Shift away from the COCl2. So again, that would mean towards the product or towards the reactants. So when you look at the change, the decrease, the gradual decrease in the product line, you might be thinking, okay, well, that's a huge spike. That gradual change is pretty gradual. Again, it's probably because the lines are already ugly and crossed once in the spike, so they probably didn't want to do it again. Okay, so we're not really concerned how much does it have to change to reestablish equilibrium. We'll do that on Thursday and Friday. Okay, so when you have 20 and 45 seconds, the reason we did those together because of the spike. So that is a concentration stress. So when you have a spike, it's going to be a concentration change. Could be increased or decreased. These both happen to be increased. The worksheet has one where the concentration is decreased, but you should be able to really see what's going on. So the other two stresses we talked about yesterday was pressure, volume, and temperature. Those ones are not directly measured on this graph. The y-axis will not change. So we are going to do it opposite. So we have to look at what is happening at 32-ish seconds and then say, okay, what are the two stresses possible? Okay, so I even wrote ish, but if you think it's, at first I was like, oh yeah, 35, but then when you look at it big on this piece of paper, it's more like 32, but clearly this graph is not well done, okay? It's just a sketch, and that's okay. Also, I forgot to write the reaction on this slide, if you want that too. So at 32 seconds, no spike. but something is happening. So I'm going to do the same highlights. Sorry, I'll go back. Oh, sorry, that's the wrong one. So the concentration lines are changing, but they are all gradually changing. The two reactants are the two dotted lines are changing in the same way, and then the product line, the solid line, is changing in the opposite way. So again, we have to follow the laws of reactions, okay? So how are the reactants changing? Are they gradually increasing or decreasing? Okay, so they have to both be decreasing, and that means automatically then the product has to be increasing. Can't be the same. So is it gradually increasing? Yes. So if the reactants are being consumed and the product is being produced, then the direction that's being favored or shifted towards is going to be the product side or right or forward. Okay, so the products are increasing, which means that they are being formed. So this direction is what's favored. So we haven't decided anything about what is changing yet. We're just saying, what does the graph show us? So we did concentration already. The other two types of stress were pressure volume and temperature. So we're going to look at both of them because we can't tell if it's which one it is exactly, because the graph is measuring concentration. It is not measuring pressure, volume, and temperature. But something is clearly happening. The lines are not level, so it could be either one, and neither is a better choice in this case, so we have to explore both. Actually, I'll write them in order, the same order as yesterday. So when we analyze pressure and volume, they go together. So again, like yesterday, if you prefer to just think of it as volume, that's fine. You're not going to get more marks for talking about pressure because it will be the same shift or the same change. So when you do volume, you have to look for the number of moles of gas. So we have gas CO, gas Cl2, both of them are gases. And then on the product side, COCl2, also a gas. So when we count the number of moles or the coefficients, we can use all the substances. So on the reactant side, there is 1 plus 1 or 2 moles of reactants. And then on the product side, there's only 1 mole. So one of the types of questions could be, if you increase the volume, which side would it shift to? If you decrease the volume, which side would it shift to? We have to go the other way. So we have decided how it's shifting to the right or forward towards the products. We can count the number of moles, and now we need to decide, is it shifting to the side with less moles or more moles? So if the reactants have 2 and the products have 1, which side is less? Product side or reactant side? Products. So it is shifting to the side with less moles. So then you're going to go backwards. So the stress must be a decrease in volume. If it was shifting left to the side with more moles, you would say the stress must have been increase in volume. So volume is sort of one, kind of requires a little bit of knowledge or memorization. Less volume, side with less moles. More volume, the side with more moles. Temperature is the one that requires the most brain power. And when you're asked, or when you're given a situation like this, then we are going to look at where the energy is for temperature. So in our case, we are given the temperature on the product, or the energy on the product side. Yes, that means exothermic, but you actually don't need to specify that, okay? So I'm going to write it like the energy is on the product side. You can write it's an exothermic system. Either of those is fine. Okay, so energy is a product. So again, we have already decided that the equilibrium is shifting towards the products. So if it is shifting towards energy, then that's what's happening, which means the stress is opposite. So if the system is making energy as a response, then the stress must have been cooled down, or the opposite, decrease in temperature. And then when you say it like that, then you can check. Okay, so if I said the stress was a decrease in temperature, the system would have to make energy, which would shift it to the right. Is that what is happening? Is that what the shift is?